unless anyone else wants to take over. Interpretive dance, everything goes. Comedy routine, we have 15 minutes to fill, you know. All right, just one more time. Is Zhixiang Shah here? Or does anyone there here on their behalf? All right, let's stretch some time, folks. It's gonna be good. right, good morning, everyone. Thanks for shaking off club night and being here on time. Congratulations to you all. And congratulations to me for being up here. Unnecessary. Thank you, though. So we're near the end of OHBM, so thank you all for populating the room, and glad we're all curious about science and the great work that we're going to show today. We have, I believe, 5 speakers, not 6, with us today. We'll be taking questions to the app. This is neurodevelopmental disorders, so just in case you hit the wrong room. Yeah, so we have 5 speakers, not 6. We'll take questions through the app, and if time permits, we can even take 1 or 2 live questions. So if you feel brave enough to use the microphone or you have that preference, please do so. Our first speaker is Chiara Casella from King's College London.
Hi everyone, thank you for coming. I'm going to present some findings from a recent study where we used quantitative MRI to assess cortical pathology in kids with drug-resistant focal epilepsy. So we know from previous studies that widespread structural cortical abnormalities can be seen in adults with focal epilepsy, and this has been argued to be due to ongoing disease processes. However, in children, we might expect to see focal rather than global cortical abnormalities because of the shorter disease duration. And importantly, most previous structural MRI studies in epilepsy have used measures like cortical volume or cortical thickness to quantify changes in the cortex in epilepsy. However, quantitative MRI can give us some more insight into the microstructural abnormalities underlying these changes. So the aim of our study was to use quantitative MRI to assess cortical abnormalities in children with drug-resistant focal epilepsy, and to do this we used a surface-based T1 and T2 relaxometry approach. So we scanned 45 healthy controls and 32 children with epilepsy, and in the patient sample the mean disease duration was 6.7 years. Of these patients, 7 had visible focal cortical dysplasias, which, if you don't know, are malformations of cortical development with very varied histopathological features, and are also the most common cause of focal epilepsy in children. And our age range for the sample was from 2 to 18 years old. We scanned them on a 3D scanner, and we didn't use sedation. We instead used retrospective motion correction, and this is just to show you an example of how this approach improved data quality. Hopefully you can see that. We then fit joint system relaxometry, and this allowed us to obtain 3D T1 and T2 relaxation time maps. So we then went on to perform cortical samplings of these relaxation times, and to do this we first performed surface reconstruction of FLAIR and T1 weighted images, and to do this we used the HCP structural pipeline. And we then created a series of cortical surface depths by sampling the surface vertices in steps of 20% of cortical volume. And this in turn allowed us to project our T1 and T2 maps to each of the cortical surface depths we created. And this in turn allowed us to answer 3 main questions. So the first one was, we were interested in understanding more about the group differences at each cortical depth in T1 and T2. And then we were also interested in understanding a little bit more about intracortical variation in T1 and T2 as an indication of intracortical microstructural organization. And finally, for those 7 patients that had visible cortical lesions, we wanted to try and compute a QMRI profile of these lesions across the different depths. And for all of these questions, we also assessed whether we could detect associations with clinical variables, and for this we used disease duration and number of seizures per year. So when we looked at group differences in T1 and T2 at each depth from the gray white matter border, we found widespread increased T2 in patients with stronger differences in the outer cortical layers, suggesting that these differences are mostly cortical. And importantly, if we restricted the analysis to patients with left hemispheric focus only, again, these differences were very widespread to both hemispheres, suggesting that the differences are not related to focus laterality. And importantly, we didn't detect an effect of cortical thickness, suggesting that these differences are probably not due to atrophy. And we didn't detect any associations with clinical variables. To assess group differences in intracortical organization, we basically subtracted vertex-wise values at the 20% depth from the values at the 80% distance. And this allowed us to assess group differences in the gradient of change in T1 and 2 values. And here we detected, again, significant differences in patients with widespread steeper gradients in both T1 and T2 in the patient group, with increasingly higher values in the outermost cortical depths. And again, we didn't detect any associations with clinical variables. And finally, to compute surface-based QMRI profiles of FCDs, we first delineated lesion masks on the FLAIR images of each of the 7 patients with FCDs. We then mapped these lesion masks to each cortical depth in patients and controls in standard surface space. And we extracted T1 and T2 values at each cortical depth within the lesion. And this, in turn, allowed us to compute a Z-score profile for each patient against the control distribution. And this here is just the pilot results showing in the colored lines the Z-score profiles for each of the patients. And basically, anything that goes beyond the red dashed lines will indicate a significant deviation from the control distribution. And in general, you can see that both within and between lesions, changes in T1 and T2 are quite heterogeneous. And this suggests that the cortical changes we observed in the previous 2 steps are likely not specific to the focal cortical lesion. Again, we didn't detect any associations with clinical variables. So to summarize, we detected global cortical damage in pediatric focal epilepsy, and importantly, these changes don't seem to be specific to the cortical lesion. And the widespread effect of changes is also not linked to clinical variables, and we think this might suggest the presence of a developmental effect rather than an accumulation of damage. And because there were no changes in atrophy, we think probably these changes represent alterations in myelin or iron, or maybe increases in free water because of edema or a combination of these. So I would like to thank all of my colleagues and all of the families who contributed their time to this research, and I'm looking forward to your feedback. Thank you.
Thank you very much. This is open for questions now. Like I said before, you can use the app if you have questions, or you can feel free to use the microphone. We'll entertain both questions in this session. Since there are no questions now, I'm going to ask a few. So great talk. Thank you very much. So just a couple of things. When you're sampling at 20% intervals across kind of the cortical surface, how does the issues of resolution, how do you deal with issues of resolution, partial volume effects in these type of data specifically? Because they'll be quite abundant.
I think we try to deal with partial volume effects, especially by making sure the registration was good. So the HCP pipeline is quite robust to that. And also, if you saw, I didn't consider the pile surface or the white matter boundary. So I just considered the bits in between, so that I think the partial volume effects are a bit less present there.
Okay. And then, I guess, in work that I've done in T1 mapping, for example, one confound is that there's those measures, at least kind of quantitative measures, are often confounded by the curvature of the cortex. So in general banks and the fundus, you see these inflated values, say of T1, because there's almost like a signal pile up there. Did you consider the effect of cortical curvature?
No, I didn't, and actually maybe that's a good covariate to add to the analysis.
Yeah.
But yeah, that's a very good idea.
Yeah, I think you just want to make sure that the actual geometry of the cortex isn't influencing your sampling at all. Yeah. I'm just going to check the app one more time. All right, no questions from the audience? I just have one more. Had you considered, I understand you started from the white matter surface and went up to the peel surface. Have you given any thought to sampling across the white matter boundary as well as kind of almost an index of transition? Yeah, I didn't
say that, but especially when we looked at lesions, I decided to go a bit deeper. So I sampled up to -1 millimeter from the white matter boundary, and that was to see some lesions are more sensitive in white matter, but we didn't really detect anything significant. And when I looked at the whole brain level at -1 millimeter, I also didn't detect anything.
Thanks. My last question. There are questions. I'm not getting a refresh. I'm sorry. Okay, thank you. I'm sorry, everyone. So one question that came up is, did you see any age effects?
Yes, we saw age effects. We didn't detect any interaction between age and group, but we did see an age effect that was consistent with the literature. So okay. Decreases in T1 and T2 with increasing age.
Okay. Is there, okay, I have one last one. Is there other evidence of widespread change in the cortex in epilepsy as well?
Is there what, sorry?
Other evidence of widespread cortical.
Yeah, so we were quite happy because recently a study was published in adults which used T2 and a similar approach to ours to map changes across the cortex, and they showed that in adults these changes are present, and the pattern of changes is consistent with what we observed, so that the changes are more prominent in the outer layer of the cortex.
Great. Okay, thank you very much.
Thank you. Thank you.
All right. All right. Our next speaker is Michael Gronevater from Carnegie Mellon University.
Hi, everybody. My name is Michael Gronevater. I'm a medical student in the MD-PhD program at the University of Pittsburgh and Carnegie Mellon. And today I'm really excited to talk a little bit about my work looking at pre to post changes in the visual system in a case of pediatric occipital lobectomy. Now, before I get into the weeds of that very specific case, I first want to talk a little bit about development of the visual system in the healthy child brain. So, throughout this talk, I'm going to be talking about changes in the visual system to support visual recognition. And we actually know from prior neuroimaging work that representations for visual categories changes over the course of development. I'm going to illustrate that here. So in young childhood, you actually have typically bilateral representations for faces. But then children go to school, they learn how to read and become proficient word readers, at which time you start to have word representations emerge in left cortex, presumably to reduce the length of connections to language regions that are typically left lateralized. And that's not to say that there aren't any word representations in the right hemisphere. There are some. But the bias is toward emergence of category representations for words in the left hemisphere, such that by adulthood, you have mostly words on the left and faces on the right. Again, with some bilateral representations of the two. So the fact that words appear to emerge in the left hemisphere over the course of development might seem to suggest that the left hemisphere would be necessary for word recognition. But we actually can answer that question with some neuropsychological data. So if you look at patients who have damage to occipital temporal cortex, or as I'll be abbreviating throughout the talk, OTC, in adults at least, who have lesions to left OTC, many of these patients end up having word reading impairments. And the fact that these patients have such specific deficits in word reading impairments with such focal lesions would seem to suggest that this patient, for instance, their ipsilesional left cortex or their contralesional right cortex isn't supporting word recognition. But again, I told you this is a segregation of function that appears to emerge over the course of development. So we can ask the question in children, like this patient who had a left occipital resection, who was at the age of 13, we can ask, can this patient's ipsilesional left cortex or contralesional right cortex support either or both visual categories? And we have done some prior work in our lab to provide a little bit of evidence for this. So previously, we had children with OTC resections on the left or right view a simple category localizer while in the magnet, and we basically mapped out category selective regions. And here's, for instance, an example right resection patient and an example left resection patient here. And I'm showing kind of their category selectivity for faces and words. And what was found in this study was that no matter which side the resection was on, category selectivity could be detected in the preserved tissue that's left behind. So if you have surgery on the left, you can show category selectivity on the right for all your visual categories. But this is just capturing patient data at one point in time. In many cases, when we do these studies in post-surgical patients, we're looking at them in some cases 2, 3, 4 years maybe after they've already had surgery. And so I wanted to answer in this study the time course of potential reorganization of visual category representations. Specifically, you can imagine that maybe the brain has already reorganized, in a sense, before a patient even goes to epilepsy surgery because of the presence of epileptic genic pathology or the presence of tumors, et cetera. So how much are the deviations in category selectivity pre-surgery, but also, is it possible for us to track changes in category selectivity pre to post-surgery and longitudinally? So to answer this question, I was fortunate enough to work with a young girl who started having seizures at the age of 6 years because of perinatal strokes leading to encephalomalacia in her left occipital lobe. And I should point out here that a good chunk of her left occipital was intact, as was her left temporal, which was completely intact. And medications were not able to alleviate this patient's seizures, so she ended up having surgery at age 13, where they removed all of occipital cortex with a little bit of parietal as well. And we had the opportunity to scan her a couple of weeks before she went to surgery, and then about 1 year and 2 years thereafter. And when she came in, what we did is we showed her a simple functional category localizer, like what I showed you previously, blocks of faces, words, houses, etc. And what I did is I measured the category selective volume, the amount of cortex that was selected for each of these different categories in her ipsilesional left hemisphere and her contralesional right hemisphere. And then what I did is I compared that to a cohort of healthy age-matched controls. And I did these comparisons, again, both pre and post-surgery. And so what did I find? Well, first I derived a laterality index where I basically compared category selectivity of the left hemisphere to that of the right hemisphere. And for those who are like me who can't do math quickly in their head, basically what this formula means is that if you have a more positive value, that means you have more left lateralization of a category, and a negative value, more right lateralization. And so this is the control data plotted here and throughout the talk in blue for each of the different stimulus categories. And just as a proof of concept, you can see that the controls showed more right lateralization for faces and left lateralization for words. But how about the patient? So the patient, perhaps unsurprisingly, showed significant right lateralization for most categories, both pre and post-surgery. Throughout this, I'm going to be labeling the pre-surgical scan with a 0 and the 2 post-surgical scans 1 and 2. And I should say that what we did is we compared each patient data point to the control distribution using a statistical test used in neuropsychology called the Crawford test to test for significant differences of a patient, single patient outside of a control distribution. And again, she showed right lateralization for all categories, and that actually turned out to be the case because she showed close to no ipsilesional left hemisphere category selectivity pre or post-surgery. So across the board, we actually ended up doing a whole hemisphere analysis to try to see if we could detect any category selectivity for any of these categories, and it was close to 0 across the board, even though we could localize it in typically developing controls, both in their left hemispheres and their right hemispheres, which I'm going to be always displaying on the left and right like that. So where was her category selectivity? It was, again, mostly in contralesional cortex. Again, importantly, pre and post-surgery, she's showing category selectivity within the typically developing range. And again, because this is occurring pre-surgery, this suggests that there's already been a push of most of these categories to the right hemisphere, even before she goes into the operating room because of her epileptic pathology. It's not necessarily, from what we can see from these data, because of her surgery. But I should point out one key, really interesting exception that we noticed, which was for words. She actually ended up showing close to no detectable category selectivity in either hemisphere, pre or post-surgery. And she only showed minimal category selectivity initially post-surgery, but then it appears she seems to show a lot of category selectivity for words about 2 years post-surgery. And so what we did is we did a fine-grained analysis where we looked at her word selectivity in these different parcels. And sorry that this came out weird on these slides. But basically here in 2, we're looking at her second post-surgical scan in her V4 and fusiform. And I want to highlight for you that not pre-surgery, not initially post-surgery, but only longitudinally post-surgery, does she seem to now all of a sudden have category selectivity in her right hemisphere for words that is above what you would see in control's right hemisphere, but is comparable to what you would see in control's left hemispheres. So in conclusion, what I showed here today is, one, that when this particular patient had occipital lobectomy, she wasn't actually able to show any sort of ipsilesional left-sided category selectivity pre or post-surgery, suggesting that changes in the brain might have already started to occur before she ever went to the operating room. Moreover, it also seems that her contralesional hemisphere is able to support category selectivity pre and post-surgery, with the key exception for words, where we're starting to see words emerge only longitudinally post-surgery in her right hemisphere. What we see as a really beautiful example of potential plasticity of the child brain, again, a single case study, but we hope that this will serve as fodder for future work investigating this question. So with that, I just want to quickly thank my co-authors, Drs. Liu, Mao, Patterson, and Berman. Definitely thank you to the participants and their families, the funding sources, and this is my email. I'll be around at the conference, and I'm always happy for a virtual Zoom chat to talk about this work, or also our cohort studies that we're doing in patients who have already had surgery with functional, structural, and behavioral measures. Always happy to chat, so please don't hesitate to reach out. Thank you for listening.
Thank you very much for the excellent talk. So if you have questions, again, in the app, or upvote the questions you like, or you can ask them yourself. So we have a few. The first that was most upvoted was, how did you control for the presence of, okay, I'm going to say this wrong, homonymous hemianopia that is known to follow occipital lobectomy?
That's a great question. It's something that we deal with quite a lot. Throughout these tasks, we instructed the patient to centrally fixate. There's been actually a number of studies that have actually shown that kids who start having epileptic pathology or surgery at very, very young ages actually adapt so that if you tell them to fixate at something, they're actually going to automatically adjust their visual field to make the whole picture in that visual field. And we had them do a task as they were doing it to see when the picture repeated, and instructed them to fixate to try to control for that. Yes.
Great.
Yeah, so more neuro-ophthalmology questions. So was there visual field loss? Was it complete? And then was there transneuronal degeneration? Did you check OCT to see what the retina looked like?
Sorry, what was that last part?
Was there transneuronal degeneration into the retina with OCT?
I don't believe, from what we saw, that there was any degeneration to the retina.
Okay.
She did have a visual field cut. Again, it was like a lot of these patients that we work with. In fact, in a lot of cases, we work with kids who have like full hemispherectomies as well. These patients will report hemianopia, and you can see it on clinical exam, but they won't actually detect it in their day-to-day life. So she did have, again, a peripheral field cut, both pre and post-surgery, but again, not something that she would have been able to tell you that she had.
Yeah, I mean, there's obviously the blind sight theories out there that the non-LGN pathway is still intact. So,
Right.
yeah.
All right, we'll take one last question here, which is the lateralization independent of the right or left-handedness of the patient?
That's a fantastic question. It's a question that we constantly struggle with, because a lot of these patients, if you start to have a lesion in one hemisphere, typically that might start to affect your motor function contralaterally. So some kids from very, very early ages, for instance, will have sorry, I always mix up my lefts and rights. If you have a lesion in your left hemisphere, you might actually end up growing up left-handed. In this case, this patient was right-handed, but it is kind of a confound that we're still working to figure out, given how it's always mixed in with the pathology. Is the pathology causing the handedness, or is the handedness related to the brain reorganization?
Great. Thank you very much. Wonderful talk.
Thank you.
Our next speaker is Sherry Shen from the University of Pennsylvania.
Okay. Thank you for the introduction, and thank you all for your interest in our recent study about generative network models for neurodevelopment in infants with and without familial risk for autism. My name is Sherry Shen, and I'm a PhD candidate at University of Pennsylvania. This project was developed at Penn Decipher Lab and also with our collaborators from the IBIS network. First, I will do a little bit introduction. Autism spectrum disorder is a broad range of neurodevelopmental condition that characterized by social communication defects and pronounced restrictive or repetitive behaviors. About 1 in 100 children has been diagnosed with autism. Signs of autism usually appear by the age of 2 or 3, and researchers have shown that early diagnosis and intervention can improve the overall development of autistic children. Autistic brains may involve atypical wiring in their complex network structures, which can be studied using diffusion tensor imaging. We can first postulate the brain into different regions denoted by nodes of the network, and then calculate the number of string lines connected to nodes, annotated by the edges of the networks. Then we can compute different network properties like network statistics from those brain networks. However, it is still unknown what wiring mechanisms give rise to early developmental diversity in brain networks. And when do these atypical wiring patterns emerge in autistic brains, and how are they related to behavioral symptoms? The goal of this study is trying to investigate these questions. We gathered our data from 4 clinical sites in the IBIS network. Infants having an elder autistic siblings are defined as high familial risk group, denoted as HR. Those without first-degree autistic relatives are defined as low familial risk group, denoted as LR. At 24 months of age, they received a-dose evaluation to determine whether they diagnosed autism. This defined 44 HR-positive subjects. 217 HR negative subjects, and 106 LR negative subjects. These subjects received diffusion MRI scans and also behavioral assessment around 6, 12, and 24 months of age. We use generative network models to study our data. In this method, we can apply different parameterized wiring rules to test whether infant's brain follows some specific wiring mechanisms. For example, we can create a simple model with the probability of forming connections between two nodes, power law decay with a distance EUV, as our brain is trying to minimize connection cost. However, cost minimization is not the only mechanism that happens in our brains, as our brain also requires certain topology to achieve functionality. So we can include a second topological term, KUV, and define the probability of forming connections as a trade-off between minimizing wiring cost while reinforcing topological features. We have two parameters, eta and gamma, controlling the influence of two terms. By varying eta and gamma, we can fit a model to different subjects' brain network. We tested 13 generative network models that were proposed by Basel 2016, including degree, clustering coefficient, and homomorphy-based constraints as listed here. For each observed brain network, we started from a seed network containing 44 edges across all subjects. We randomly sampled eta and gamma parameters and generated new edges one at a time based on the probability PUV until the generated network reached the same sparsity as the observed network. Here, I want to highlight the matching index model, which calculates the overlapping rates of neighbors between two nodes. This model tends to connect nodes sharing similar neighbors in addition to cost minimization. If we look at nodes in the red box, the lower two nodes may be connected if the model weights a lot on the geometric parameter eta. By increasing the influence of topological parameter gamma in the matching index model, it may shift to favor the upper two nodes that share more neighbors. Previous studies have found that matching index model is the optimal fitting model in healthy adult brain and also school-age brains. It would be interesting to know if this model can also explain infant's brain. What makes the differences between different risk and diagnosis group for autism, and when do these differences emerge? We use an energy function to measure the fitness of the model, which calculates the maximum Kolmogorov-Smirnov statistics between generated and observed networks in terms of their degree, edge length, clustering coefficient, and betweenness coefficient. A generated network with a lower energy means that it is more similar to the observed one. So for each observed network, we randomly sample 10,000 points at the parameter space to obtain the eta gamma parameters that are associated with the lowest energy. We repeat it again with a much narrower searching space around the parameter obtained from the previous steps. And we use the average score of the top 1% lowest energy networks for the evaluation. The model parameters were then harmonized across different sites using a structural causal model. We found that the matching index model is also the optimal fitting model for all three groups, and no group differences were identified between HR positive, HR negative, and LR negative in terms of their model fitness. Also, we compared the energy among different visits, and we found no group differences among them. This means that in early development, brain networks tend to connect nodes that share similar neighbors in addition to cost minimization. And we can use a single model, the matching index model, to explain all the time points, all risks, and diagnosis group equally well. So next, we analyzed the longitudinal trajectories of the model parameters in different groups. We found that HR positive has a decreasing trend in gamma and also the magnitude of eta, while HR negative and LR negative have relatively stable gamma and eta. As decreased magnitude of eta will cause less spatial constraint in the network generation in the HR positive group. This may be associated with longer fiber length and also brain enlargement in the autism that were found in previous study. Decreased gamma also means less homophily attractiveness, which may be related to reduced modularity in autistic networks found in previous study. We found group differences between HR positive and LR negative at 12 and 24 months in gamma and 24 months in eta. Meanwhile, HR positive and HR negative show group differences at 24 months in eta. HR negative and LR negative show group differences at 6 months in gamma. We plotted the trajectories of different groups in the parameter space, and we can identify the typical developmental trends since 12 months old. We further analyzed the relationship between model parameters and behavioral scores using mixed effect linear model, controlled for sex, age, size, and scan motion. We found that eta is significantly positively correlated with Mullen's gross motor and violence socialization score. Gamma is positively correlated with Mullen's gross motor and receptive language score. So in conclusion, we tested 13 generative network models and found that matching index model can best characterize early development irrespective of risk and diagnostic status, and it can explain all time points equally well. Atypical wiring patterns in autism can emerge around 12 months old, and the changes in generative model parameters may be related to some previous findings, such as longer fiber length, brain enlargement, and also reduced modularity. These atypical wiring mechanisms are also associated with early motor, verbal, and social behaviors. And feel free to stop by our posters today for more detailed results. And we also have another work using deep learning with the generative models to model the brain development if you are interested. And of course, I didn't do all this alone. I want to thank my advisor, Ragini Verma, and also our amazing collaborators from the IBIS network for their contribution to this work. And I want to thank everyone for your attention, and please connect with us if you have any interesting thoughts. Thank you.
Thank you for a very interesting and wonderful talk. I have one question in the app, and I have a few questions of my own. Can you speculate as to why you don't see atypical wiring patterns earlier than the 12-month period?
One reason is because it may suggest that the atypical patterns of autism may emerge around that time. Because there's also some literature in this infant data, and they also started to identify, for example, the white matter changes around 12 months old. So that may be associated with these findings as well.
Okay. Again, if you want to use the microphones, please go ahead. I have some other kind of data processing questions for you. Mm-hmm. How do you deal with motion in a cohort like this, so it doesn't become a confound in
yes,
the
yeah. So we first analyze the scan motion, and then, for example, when we do the mixed effect linear model, we just controlled for the motion parameters.
So were there any triage of individuals from the study due to motion or certain time points? Or do you keep everyone regardless?
For different time points, there's no statistical significance across different time points.
Okay. What was the male-female ratio in the participant group? And did you see any sex differences, or did you look for them?
So in this study, we combined male and females together. But for the analysis, we also controlled for the sex effects. So the correlation I showed is controlled for sex. Yeah, but it is do have differences in male and female, especially for autism, because it's male mainly disorders. And but for the in terms of the model fitness for the generative models, the match index is also the is also the optimal for the fitting models for both groups, and there's no group differences in terms of the model fitness. So in that case, we can just use the parameters and then analyze the parameters after controlled.
Right, but were you balanced for sex in the study, or
What?
were the groups balanced for biological sex, or was it skewed towards males, or what was that?
It's so because usually there's more male in male autisms used for the autism disorders. There's more male than female.
Right, but can you tell us about your sample?
For the samples, it combined the two, but when we do the analysis, we controlled for the sex effects.
Okay. All right, thank you very much for this talk. Our next speaker is Kanad Manki from the University of Cambridge.
Thanks a lot for sticking around. We'll get over this hangover together. Just before I begin, I want to give you a little context for this project. So around this time in 2019, we started a large-scale dyslexia study, longitudinal study. So recruited about 130 participants. And then 6-8 months later, this little guy called COVID arrived, and we couldn't get the longitudinal data. So what the data that I have today is from the baseline period, sort of really high-quality artisanal sample. So dyslexia is a learning disorder. As many of you know, that it's characterized mainly by difficulties in acquisition of reading and spelling. And the core cognitive phenotype is phonological deficit. It affects about 3 to 7% school-age children. So I'm not going to dwell a lot into this, but basically the idea is that with phonological deficit, the children have difficulties manipulating sound structure. And then that translates into reading difficulties. So a bit of background on basics of sort of auditory processing for those of you who are not familiar with it. Auditory cortex is a very sophisticated structure. So it allows us to track incoming information at a very precise time scale. So even as you're listening to me now, hopefully the neural oscillations in your auditory cortex are entraining to the speech rhythms that I'm producing. So if I start speaking fast, the oscillations are going faster. If I start speaking slower, the oscillations also change in rate. And the way this mechanism works is tracks something called as an amplitude envelope. And it's generally in the sort of low frequency region, sort of delta theta range. Particularly in dyslexia though, it's not quite clear whether the deficits we see are mainly in the low frequency region or the high frequency region. So there's a lot of debate in the literature. If you look at the adult dyslexic literature, everyone often goes on about gamma band, but in children, you don't really see that sort of really strong activity. And it's also something that develops from childhood to adulthood. So particularly in speech and noise environments, if you want to identify a particular speaker, it's usually the envelope tracking in that direction that improves and extracts information from background noise. So we sort of need to take sort of a rhythm-based approach to this. That rhythms sort of do exist in our brain, but also in the speech production. So the coordination of all my oromusculature is also rhythmic. The articulators that are producing all these sounds are also rhythmic. And there are lots of these wonderful studies looking at large corpuses of data from different languages. And what you see is that they all have very similar statistical structure, right? So on the x-axis here, we have frequency. And these are languages of very different origin. So Marathi being my mother tongue there, but you also have Japanese, which is sort of overlapping with each other. And you generally get a power spectrum around the region of 3 to 4 hertz. But when you look more closely, what you see is that you have some individual variations between languages, but it's relatively rate restricted. And the reason for that is all of us have the same oromusculature. It's not the case that people from certain cultures will suddenly speak a lot faster or produce completely different frequencies. Right? So we're quite rate restricted in that sense. So it makes sense to think that then our brains are also evolved to understand this mechanism quite well. So generally, in a lot of these speech entrainment studies, what tends to happen is that the people who are interested in looking at how speech features are mapping onto the brain, you take the source time series from your MEG or EEG data, you take the speech envelope of whatever the stimulus that you're presenting, you filter them in the same frequency band and measure some sort of statistical dependence. So if I filter both of them in delta band, I'm trying to impose any linguistic features on top of the delta band, which is not a very precise approach. So there's a lot of work on this, and we use this model called spectral amplitude modulation phase hierarchy model. What it basically shows is that all the speech rhythms are sort of indexed on top of each other, and there's a tight phase relationship between them. So there's just a toy example here. We've got two words, comfortable and debatable. Both of them have very distinctly different stress pattern, and when you put it through this model, it's going to extract some prominent features in the data. So the low frequency being the stress rhythm, which is immediately different there. And then you have syllable rhythm that goes from about 2.5 to 12 hertz, and then phoneme, which is sort of your beta gamma. But the idea is that this tight phasic relationship is sort of multiplexed, and that's what allows us to have a complete percept of it. The way to obtain this is quite simple, actually. You start with your sort of original waveform, whatever your speech material is. You filter them in cochlear frequency bands. These are very narrowly defined filter bank. And then you perform, you take the speech envelope of that, and then you perform a spectral PCA. And what that gives you is the sort of three main mode of variations in the data. So the one that's shown here in red is your stress AM, the one on top there. Then you have syllable AM, which is in green, and phoneme, which is in blue. Now coming back to dyslexia, what we wanted to test is what is this locus of deficits that we see in dyslexia, which sort of oscillations are there, which brain regions are involved, and are there any functional differences between them. So this is the sample, a small subset of our cohort that we have. There are 20 participants in the control group, 19 in dyslexics. The eagle-eyed among you would have noticed that the dyslexics are slightly older, but that's actually a good thing, because that just means that they've had slightly more time than the controls in terms of reading experience. But you'll see that they're all still quite poor on reading scales compared to controls. So we do a large battery of tests when participants come to our lab. We do resting state scan with MEG, a naturalistic story listening paradigm, and then they do a few more experiments. We also acquire structural data. But for just the purpose of this talk, I'm only going to be talking about the resting state scan and the story listening paradigm. And we obviously use the anatomical data because we need it for source localization. So it's a 10 minutes naturalistic story listening paradigm. It's a children's story called The Iron Man by Ted Hughes, Sylvia Plath's husband. And we put this material through the SAMPH model. It gives us 4 frequency timescales that are sort of prominent in the data. One is the stress AM, the syllable AM, and then the phoneme. These are mainly the ones that we get, but we also see a local maximum right about there, which is the subbeat. And that's usually when it's a speaker characteristic, so it's not always present there in the data, but when you want to compress multisyllabic words together, you tend to speed up your rate of speech, and you get activity that looks like that. So the first contrast that you're going to see is story listening compared, again, resting state. In terms of statistics, it's always the same approach throughout this talk. So I always use non-permutations statistics test. So the scans between the groups are permitted 5,000 times. You create a distribution, and you measure your data against it. And it's obviously corrected for multiple comparisons. And so this is what we get. So we have stress, syllable, subbeat, and phoneme. The controls are on my right-hand side and dyslexics here. For stress AM, what we see is a pretty nice auditory cortex localization activity sort of in the auditory belt area. In the dyslexics, it's very sparse activity. And it's not the case that the children are not listening to this rhythm at all, but it's just that their neural oscillations are not significantly different from when they're listening to a story versus when they're at rest. Then at syllable AM, we see lots of activity predominantly in the sort of language network, which is what we would expect. lots of activity in the auditory cortex and frontal regions. Again, for dyslexics, what you see is that the activity in the auditory cortex is particularly sparse. And so it's almost the case that to achieve the same decoding task, they're recruiting additional resources from other parts of the brain. Subbeat AM, as I said, that this is not a language universal feature as such. It was just there in the data, so we didn't really expect any specialized neural mechanism for it, but we found some source localization in the superior parietal region. In adult literature, it's been shown that this is sort of the region that's involved in keeping time of incoming stimulus, so it's updating predictions. But of course, in a naturalistic paradigm, you can't really test those hypotheses. In the phoneme AM band, again, you see activity that's localized in the auditory cortex, but very sparse or if not nearly absent activity for dyslexics. The next thing is a group comparison, so controls compared against dyslexics. Here, the positive values indicate that controls exhibit a higher activity compared to dyslexics. And the interesting result is really this one. The activity is really localized in the sort of lateral occipital region. In adult literature, if you look at it, it's almost left lateralized. So it's almost the case where adult dyslexics have years of experience converting phoneme information, sort of written text into phoneme information, which children obviously don't. So it might be the case that this is a developmental effect, which we might be able to see in our sample if we get some participants this year. So we then, based on that, identified 13 regions of interest within which we calculated something called as phase locking value, just measures phase relationships between two frequency bands, the stress and syllable AM band, because that's where we saw the biggest difference. So we have controls on top, dyslexics at the bottom, the stress, syllable, stress, and syllable. These are sort of the average maps, but straight away the thing that you see that dyslexics show a very sparse connectivity. There's very little hemispheric, intra and interhemispheric connectivity there, and which is what we see when you do a statistical comparison. So if we take the example of, for example, say right superior temporal gyrus, we see very little connections originating from there going across hemispheres, but which we do see that in controls. We then put these individual maps through, and we just calculate a simple graph theoretic measure called global efficiency, which is a proxy measure for how information is integrated in the network. And we see very clear difference between controls and dyslexics. The global efficiency measures are also correlated with BPVS, which is a standardized measure called British Picture Vocabulary Test, where the tester essentially just shows pictures, says out the word, and the children have to point it out. But again, I'm acutely aware that this is a small sample study, so these correlations, you shouldn't really take them to mean anything more than they really are. We also don't have any normative data on these sort of relationships, so just a word of caution there. So just to summarize, the main differences in children with dyslexia and controls are particularly in the low frequency bands, the stress and syllable AM. They also show high frequency gamma band differences, but those are right lateralized rather than left, which is what the adult literature will tell you. And there is a marked reduction in inter and intrahemispheric connectivity. And with that, I think I'll stop. These are the people that are involved on the project. Sheila, particularly, she was supposed to come, but couldn't. She's the one who did the speech modeling work. And that's it. And the paper is also published in your image, so if you want to scan the QR code, you can read it later. Thank you.
Thank you very much. Wonderful talk. There's a couple of really nice questions in the app, and again, if you have questions, please use the microphone if you don't feel like using the app or if your thumbs are impaired. So first, do you think brain stimulation to these cortical areas could improve these measures for dyslexic participants?
So there's only one paper in adult dyslexics which has shown that there is some benefit of TMS. But yeah, that's precisely one of the reasons why we wanted to do these analysis is to identify potential target sites for remediation work. So that's one thing that we will be actively pursuing later.
Just quickly pursuant to that, is there any evidence of kind of personalized connectomes in these individuals, like we saw from Andrzej Zaleski yesterday, that you think would be of use?
So that's one thing that I do plan to do, because we do have the DTI and MEG data across frequency bands. So that's something that I'll be looking into, because I've done some work with multi-layer networks before, so that would be the idea that it's a natural extension of that.
So this came early on in the talk. Is the speech envelope unique for speech, or do the oscillations reflect music or rhythmic noises?
Sorry, say that again?
Is the speech envelope unique for speech, or do the oscillations reflect music / rhythmic noises?
So that's a good question. So if you, there's some very little work on applying these modeling work to music as well across different genres. There's a preprint from a lab. Tatsuya Daikoku is the first author, Usha Goswami, the last one. So you can look it up. And you see across genres, you see very similar statistical regularities in music as well. So it's not the case that the envelope is exclusively used for speech, but it's most likely also a mechanism involved in music perception. I'm just not familiar with that literature. So
I think we have time for one last one, which is it's an interesting question. Do you think the sex / gender of the story reader or qualities relating to their speech production may change your results?
Don't think so. Generally, with a lot of auditory neuroscience literature, female speakers are generally used as the story material, so stimulus material. I'm not entirely sure what the reasons are, but because it's as I said, that we're measuring statistical regularities in the signal, I'm not entirely sure if those would be hugely different between, say, a male versus a female speaker. Of course, you get smaller differences between male and female speakers, like form and transitions, for example, but those are not the differences that we are looking at here.
Okay. Great, thank you very much.
Thank you.
For those of you who came for the second to last speaker, Zhixiang Xia, we don't have any content for the speaker today, unfortunately, so we'll be moving ahead to our final speaker of the session, Tuan T. Nguyen from the National University of Singapore.
Hello, so I'm Tuan Ting from the National University of Singapore, but you can call me Sophia. So today I'm honored to present my project titled Variations in Functional Gradients Relate to Dimensions of Psychopathology in Preschool Children. So as you all know, young children can suffer from mental health symptoms, while the peak age of onset for having any mental health disorders is 14 years. First onset of mental health disorders can happen as early as 4 or 5 years of age. However, little has been done to study the psychiatric risk as well as the associated imaging phenotypes in preschool children. There's also a high comorbidity problem that confounds the field of study. So talking about ADHD as an example, 67% of kids with ADHD have at least one co-occurring disorders. Therefore, there have also been great interest in defining and characterizing the underlying features across disorder instead of looking at each of them separately. There are studies attempting to link disorders with functional brain patterns in children. The idea that there were both common and dissociable markers associated with dimension of psychopathology has been reiterated in many literatures, where we saw a common overarching general psychopathology factors, as well as different cognitive patterns that are associated with different dimensions, such as externalizing, internalizing, mood, psychosis, fear, etc. So as this study have mainly focused on children aged 9 and above, we think it would be helpful to look at how these neuroimaging markers might manifest itself in preschool children. Okay. So aside from directly looking at functional connectivity, there has been a rising interest in studying cortical organization as continuous gradient. So using gradient, spatial variation across the cortex is examined along overlapping organizing axis. So areas with similar gradients value would have a similar connectivity patterns. So previous studies have shown that the principal gradient that explains the most spatial variation in human display a sensory motor to transmodal cortical organization. So multimodal networks such as the default mode networks, the control networks, lie at one end of the spectrum, while the unimodal networks such as the somatomotor and visual networks lies in the opposite end. So we observe the same pattern not only in functional connectivity, but also in various data domains such as intracortical myelin, semantic category processing, etc. So that's the first gradient. For the second gradient, it separates the unimodal networks between the visual and somatomotor regions. However, all these patterns were obtained in cognitively healthy adults. So in a recent study leveraging resting state fMRI scan in healthy individuals aged from 6 to 17 years old, we note that the transition from childhood to adolescence is reflected in the gradual maturation of gradient patterns across the cortical sheet. So in children, the order of the gradients is flipped compared to adults. So the overarching organizational gradients is anchored within the unimodal regions, so between the visual and somatomotor regions, whereas the second gradients separates the unimodal and transmodal networks. So conversely, in adolescence, the principal gradient of connectivity transition into a more adult-like framework with the default mode network at the opposite end of the spectrum from the primary sensory and somatomotor regions. So, however, the gradient patterns in preschool children, the longitudinal changes in individuals' connectivity gradient, as well as whether variations of gradient patterns relate to psychopathology remains to be seen. In this study, we hypothesized that the principal organizing axis of cortical gradients would lie in the unimodal network for preschool children. We expect that different networks would segregate along the gradients between 4.5 and 6 years old. We also think that different mental health disorders will also correlate with different network gradient patterns. So for this project, we'll be using the resting state fMRI scan from the GASTO dataset from Singapore. We construct a functional connectivity matrix for each of the resting state scan from 4.5 and 6 years old. And then we can derive the gradient patterns and map them to the 7 functional networks. From there, we can look at the gradient patterns at each time point and then investigate the longitudinal changes in connectivity gradients within the same individuals. We'll be using the currently available questionnaire data at 4 or 5 years old, which assesses a few common psychiatric diagnoses and correlate them with the gradient patterns using the multivariate partially square approach. So now I move on to the result sections. So in this plot on the left, you can see that we have the principal gradient plotted onto the brain surface. And the panel B, we have the distributions of gradient values as summarized into 7 networks. We can see that clearly that gradient 1 separates the unimodal cortices, so between the visual and somatomotor regions. So the 2 panels on the right, the panel E and panel F, further demonstrate this. So this panel plotted the gradients into Euclidean space. We can see that the blue regions correspond to the somatomotor networks, and the green colors in the visual networks are on the opposite spectrum of the principal gradients. So this confirms our hypothesis that the principal gradient in preschool children is anchored within unimodal regions. So for the second gradient, we can see that it's similar to the principal gradient in adult. So this gradient separates the unimodal regions as well as the the unimodal regions as well as the transmodal regions. So with visual and somatomotor networks on one end of the spectrum, and the default mode and control networks on the opposite end. So this again demonstrated on the panel here, where we saw that the green color and the blue colors correspond to the unimodal networks. It's the opposite end of the spectrum of the red color regions, which correspond to the transmodal networks. Okay. So after identifying the gradient patterns in 4.5 years old, we then look at the functional gradient organization at 6 years old. We can see that the organization of network gradient is very similar across the 2 age groups. And then further on, we look at the 3 to 7 subjects. We have scans at both age group and carry out a paired t-test to see whether specific networks will change with age. And note that for gradient 1, the somatomotor and control network is different at 6 years old. However, this difference is quite small and does not withstand FDR correction. We then also investigate the individual correlation in the same 57 subjects and saw that the correlation are very high for the first 2 gradients. So this means that the functional gradient organization is highly stable in this preschool age group from 4.5 to 6 years old. And this lends credential to the school of thought that this functional gradients is actually a stable trait, and therefore we think that it's even more meaningful to see how this functional state might change with respect to different mental health conditions. Okay. So we then carry out the partial least squares correlation analysis to look at the pattern of gradient at 4.5 years old relating to different mental health disorders. So we discover one latent variable linking the second gradient, separating the unimodal and transmodal networks with mental health impairments. So in the first plot on panel A, we note that there are three disorders were identified to be significantly correlated with the latent variable based on the bootstrapping. So attention deficit, hyperactivity disorders positively correlated with this latent variable, whereas social phobia and specific phobia exhibited a negative correlations. So looking at the bootstrap ratio for each of the brain networks, we see that multiple networks significantly contributed to these latent variables, with the regions clustered at the unimodal areas, so like the visual, somatomotor, dorsal attention, negatively exhibit a negative bootstrap ratio, whereas the regions at the transmodal areas are positively associated with this latent variable. There was a positive correlation between the impairment and the brain scores, and this showed that there was a diverging pattern of gradient distribution across different disorders. So let's just visit the gradient patterns again, and from here we can see that children with higher ADHD impairments exhibit a more diverged network structure, where the multimodal and unimodal networks are situated further away from each other. So on the other hand, those with higher phobic scores display opposite patterns, where the networks are more clustered among this gradient. So the dorsal attention networks are also identified to be the most reliable contributor to this latent variable. So to conclude, so from our findings, we saw that the principal gradient is indeed anchored within the unimodal regions in preschool children. We also observe how functional gradient organization is highly stable in preschool children between 4.5 and 6 years old. Looking at the link between functional gradients and psychopathology, we noted dissociable patterns of gradient variations corresponding to different mental health disorders, where the gradients separating the high and low order networks at 4 or 5 years old display a diverging pattern across disorders. So our finding highlights the importance of studying functional network topography changes in children and how they might account for the severity of different mental health disorders. So with that, I've come to the end of my presentation. I would like to thank my supervisor, Professor Helen Cho, for her guidance and support, as well as all the lab members for all the advice and discussions we have regarding this project. So I would also like to thank our collaborators from the Gastro Research Group, who have generally shared the data sets with us, without which this study would not be possible. So finally, thank you to all the audience for listening, and I'm happy to take any questions. Thank you.
Thank you very much. That's a fascinating way to put the gradients to use in terms of kind of early emerging psychopathology. There's some questions on the app, and again, please use the microphones if you're so inclined. So one was a methodological question, the first one that was posed. Do you use a predetermined number of gradients, or maybe another way of asking it is, why did you only look at 2 gradients in this analysis?
Yes, so the gradient analysis actually extracted top 10 gradients, but we only took the top 2 gradients because those 2 are the ones that explain the most spatial variation across the cortex, so explain the most patterns of functional connectivity. And as you probably know, these 2 gradients also have the most well-established interpretation. So we want to focus on those with more established interpretation before focusing on the gradients at the lower end of the spectrum, where we are not certainly sure of how we might interpret them. Yeah.
Great. The next one is a methodological question as well. Is the use of 400 regions of interest reasonable in this age group, given the brain size?
Okay. So we actually also look at a smaller, more, more granulated population, so 140, and the results stays pretty much similar. So I think the choice of population shouldn't affect the results so much. Yeah.
I mean, in fairness, the brain volume should be about 80-90% of the
Yeah,
adult by
that's
then
true.
anyways, right?
Yeah.
It's not far off. And then I think one more. Elegant work and very clear presentation. Have you looked into other age groups or other cohorts?
Other issue, that would be my future work. So currently, I'm also looking at the older age group, like adolescents, looking at psychosis, as well as I'm sort of kind of dipping my toe into the UK biobank data sets, just looking at the middle age group, kind of looking at this whole lifespan spectrum. The Gusto data set itself, we are still collecting data, so the more data is incoming, and I'm looking forward to looking at them as well. Yeah.
I have one question.
Sure.
So the separation you see between ADHD and I guess anxiety disorder and social phobia, was that expected, or did you expect them to be, like, 'cause they're clearly separated in kind of that dimension. Was that an expected separation given the literature, or is that a novel finding?
I would think that in a way it is kind of in concordance with priors in previous literatures, because ADHD, as you know, like usually is characterized as externalizing behavioral disorders, whereas phobic disorders are more like exhibiting a more internalizing kind of symptoms. Yeah, so I think it's quite in accordance with previous literatures. Yeah.
Great. Great. Thank you very much for a wonderful talk, and thank you all for your attention and participation this morning. Enjoy the last few hours of OHBM, and we'll see you all in Montreal. Take care. Thank you.